Okay. So the next paper is Materials for the Masses, SVBRDF acquisition with a single mobile phone image. And the work is from UCSD and Adobe Research, and the talk is going to be given by Zhengqin Li.
Thank you for the introduction. Today I will present our work on reconstructing spatially varying BRDF from a single image. Sorry. Okay. So image formation is a complex process. The image formation is a complex process. The appearance of the image is a combination of the lighting, geometry, and the materials. Disentangling the image into the intrinsic properties is one of the most fundamental problems in computer vision and computer graphics. It can benefit many applications, including the 3D design, the rendering, augmented reality, and 3D reconstruction. Historically, there are many methods working on this problem. Previous methods can be evaluated based on two standards. One is their acquisition complexity, and the second is their generalizability and the accuracy. Previous BRDF reconstruction method can be roughly divided into the three categories. Traditional BRDF acquisition method requires to density sample from different view and the lighting directions. This method can capture accurate BRDFs, but may need expensive calibrated devices, which greatly limit their usage in practice. Some recent model-based methods represent BRDF using low-dimensional models, so that few samples are needed for the reconstruction. They use the simplified assumption like homogeneous or the stationary BRDFs, and the no lighting or geometry. This reduces their acquisition complexity, but also limits its performance. Inspired by the recent success of deep learning for a variety of vision and graphic problems, recent works have looked at CM-based method for material recognition and reconstruction. The goal is to reconstruct the materials from single image captured under the uncalibrated conditions. While this is highly practical, this method still makes strong assumptions on the material properties that may lead to poor results. In our work, we want to return the easy acquisition effort of this method, but improve the accuracy. Here we show one example of the materials reconstructed by our method. Given an image captured under the controlled environment light, our network reconstructs the diffuse albedo, normal, and roughness of the input material. Then we render the materials by placing a point light source at the same location of the input flashlight to produce an image that is very similar to the ground truth. So how can we capture complex materials with little effort? Three components can make it become possible. First, a lightweight image acquisition uses the flashlight. Second, a high-quality spatially varying BRDF the dataset. And third, a physically motivated CN architecture which is customized for spatially varying BRDF reconstruction. We will go through the three components step by step. Starting with our image acquisition method, we capture the images using a mobile phone with a flashlight. This has several benefits. First, it is easy to acquire. Every mobile phone has a camera with flashlight can be used to capture the materials. Second, it simplifies the illumination conditions by removing the shadows and complex lighting, and makes the BRDF reconstruction problem much harder. Third, The flashlight allows us to observe the high-frequency specular highlights, which are very important for material reconstruction. We also need a large-scale materials dataset to train a powerful neural network. Previous dataset do not meet our requirements. For example, the MER dataset contains 100 high-quality captured materials. However, it's a relatively small dataset with homogeneous BRDF only, and therefore cannot be used for spatially varying BRDF reconstruction. On the other hand, OpenSurface is a large dataset with spatially varying BRDFs, but the BRDFs there are not of high enough qualities to capture the rich appearance of the real world. Therefore, we train our network on the Adobe stock materials dataset, which contains of 688 kinds of materials with high resolution, spatially varying BRDFs. Part of the dataset is created by the artist, while the others are captured using a scanner. The appearance of the dataset is represented by a microfuzzy BRDF model. For each material, it has 3 BRDF parameters: the diffuse albedo, normal, and the roughness. Based on their appearance, these materials can be further classified into 8 categories, which cover a huge range of materials for the real-world the surface. We further augment the dataset by randomly rotating and cropping the image to generate the image patches of different size. To better model the real-world environment, we render the images both under the point light source and the event map. The final image will be illuminated by a combination of the dominant point light and an event map. Our basic the network has an encoder-decoder structure. It consists of a single encoder and 3 decoders, which reconstruct 3 spatially varying BRDF parameters: the diffuse albedo, normal, and roughness. The intuition behind using a single encoder is because different BRDF parameters are correlated. Therefore, the representation learned for one parameter should be also useful to infer the other parameters. Since we use the flashlight, the distribution of the light intensity is closely related to the pixel location. To handle this, we augment the input with the distance of each pixel to the center of the images. Our loss function consists of the L2 loss of the 3 BRDF parameters. Different parameters affect the final appearance of the image in different ways that are not captured by the L2 loss of the parameters. Since we hope to reproduce the appearance of the materials, we add an in-network differential rendering layer, which takes the SVBRDF parameters and the light position as input, and renders the image of the material. We define a rendering loss to be the L2 the distance from the image rendered from the ground truth BRDF parameters and the estimated BRDF parameters. Since the rendering layer is differentiable, the gradient can be backpropagated to train the network. Since the tasks of material classification and the BRDF reconstruction are correlated, combining the material classification may help BRDF prediction. Therefore, we add another component to our basic structure to do material classification. Here is our structure. Given the highest level feature from the encoder, we send it to a classifier to predict the material type. Then we use the results from the classifier to average the BRDF parameters of different materials to get the final output. We add the classification loss to be the loss function to jointly train the material classification and BRDF reconstruction. For most examples, our network can already give a good estimation of the BRDF parameters. However, there are some difficult cases where the current structure cannot handle well, such as the saturation caused by specular highlight. We found that by adding a kinetic dense CRF customized for this application, we can actually improve the BRDF reconstruction, the accuracy. Please refer to our paper and supplementary material for more details. Here are our results. We first show our results on the synthesized dataset. Given the input, our network predicts the following diffuse albedo, normals, and roughness. When compared with the ground truth, we can see that our results capture the spatially variant diffuse albedo, the flat normal, and the roughness quite well. In fact, our predictions are accurate, so that we can predict the BRDF parameters to render the appearance of the surface under normal lighting. Here we show another example. Even for materials with a relatively complex surface geometry, our method can successfully generate accurate BRDF reconstruction. Here we show a range of BRDF reconstruction on the test set. For most materials, the reconstruction results are very good. For more difficult materials, even though the artifacts can be observed near the complex geometry and the specular highlight, our method can still produce a reasonable BRDF reconstruction. Actually, this is one of the examples with high error in our test set. Here we analyze the effectiveness of different modules of our framework. We first quantitatively compare the network trained with the images rendered with only the event map and the images rendered with the point light source, which justify our choice of using the cameras with flash to capture the data. Then, we verify our design choice through both quantitative and quantitative comparison. We first show that adding the material classification can help the BRDF reconstruction. And then we show that adding the cascade density kinetic CRF for post-processing can also improve the performance. One interesting phenomenon we observe is that by combining the BRDF reconstruction loss, the classifier can actually achieve much higher classification accuracy, which suggests that the feature learned for BRDF reconstruction can also be useful for material classification. Now we compare our method with previous two-shot BRDF reconstruction method. Given a simple images illuminated by the flashlight, our method can reconstruct the BRDF parameters of the input images very similar to the ground truth. While for the two-shot method, an extra guidance images under the ambient lighting is needed for BRDF reconstruction. However, the estimated diffuse albedo of the two-shot method is not as accurate as our method. Notice that the two-shot method can only work for stationing the texture and may require several hours for optimization, while our method can produce results immediately with a single image without such the limitation. Here we compare our method with Li's SIGGRAPH 17 paper and the commercial software for BRDF reconstruction. Compared with the ground truth, our method correctly captures the specularity of the materials, while at the same time is robust to strong image gradients and the estimation. Here we show the results on real dataset. In the first example, given the input, we first predict the BRDF parameters, and then we render a new image using the flashlight. Our network successfully recovers the detailed geometry of the surface. The next example has similar good performance. Notice how our network successfully captures the spatially varying roughness of the materials, which is in general very challenging in practice. So previous results are captured by the Huawei P9 phone. However, our network can also generalize to the other devices. Here we show the results captured by the iPhone 10 and the Google Tango. Notice that we do not fine-tune our network, so the exact same network can generalize well to different devices. which shows that our data augmentation successfully helps the network factor out the variation across the devices.
So,
So sorry.
the results look really great, and we appreciate those, but we're really out of time at this point.
Yeah, so I think there's something wrong with the presentation system, so I actually cannot see the...
I think we have to stop.
We have to
Yes, sorry.
stop. Okay. Well, let's thank the speaker. Is there any quick question? Otherwise, I think we're really out of time and we'll leave it here. Okay. Let's thank the speakers of the session again. And thank you.